Hi students, just wanted to go through some of the things that the class talked about on the Zoom discussion, kind of the online office hours. So a good problem from chapter 14 is number 113. That has KOH, KNO3, KCN, ammonium chloride, and HCl. And you're being asked to organize these guys from most acidic to least acidic. So essentially the lowest pH to the highest pH. Okay, so KOH, these are all aqueous, breaks up into K plus and hydroxide. This one's K plus and nitrate, K plus and CN minus, ammonium ion and chloride, and HCl, strong acid, right? H plus, Cl minus. Okay, so KOH, strong base. HCl, strong acid. So those are clear cut. And then we have the salts in the center. So KNO3, K plus is group 1A, so that is neutral. I'll just cross it out. Nitrate, conjugate base of a strong acid. So that guy would be neutral too. So this would have a pH of 7. K plus, we'll ignore. CN minus is the conjugate of a weak acid, so that's going to have basic properties, but it's going to be a weak base. Cl minus, conjugate of HCl, so that one's neutral. And NH4 plus, conjugate acid of a weak base, so that's going to be acidic, but weak. So now if we put them in order, from the lowest pH would be the strong acid, followed by the NH4Cl. We have our basic one. Neutral, not basic, neutral. Then we have our weak base. And then lastly, our strong base. Okay, next up, chapter 15. Number 25. I won't work these out, but I didn't work them out in the class either. I just want you guys to think about how important the setup is. So it's asking for the pH. The first one is 0.100 molar propanoic acid. And I'm just going to abbreviate it as HPR. And it has a Ka of 1.3 times 10 to the negative 5. Then it's asking us to calculate pH, 0.1 molar, of just a salt of that conjugate base. Oops. Sorry. So let's see what it has. I think it's sodium. Yeah, sorry. Then it has pure water. And then lastly, it has a mixture of the weak acid and same concentration of the salt. So that's just would be the PR minus essentially. So on these for the salts with the conjugate base, just ignore the sodium ion part. Okay, let's just talk about them in concept. The first one is just a weak acid, right? So you'd end up with your ice chart, and then you would simply set it equal to the Ka. The 0.1 molar of the conjugate base, then that's a weak base, right? Because it's the conjugate of a weak acid. So we would have another ice chart again. But this time it would be set to Kb. And we'd find Kb from dKW and Ka from part A. Okay, pure water, neutral. And then the last one there is a mixture of the weak acid with its conjugate. And so in that case, that is a buffer. And the easiest thing to do with buffers is to use the Henderson-Hasselbalch equation, which is pKa plus the log of the base over the weak acid. And so you'd have to find your pKa from the Ka up here, and then plug in your values for these concentrations. So I'll let you find the pKa. And just like you've been learning in lab, when the concentration of weak acid and conjugate are the same, pH equals pKa. Okay. And then lastly, there's one really important one, that's number 48 in chapter 15. The conceptual piece is that the ratio of A minus to HA, this ratio determines what pH your buffer is at. So let's keep that concept in mind. So for number 48, we want to know what volume we have A minus at 0.50 molar. We have another one. Boy, my flasks are so funny. So we have the weak acid, and then we have the conjugate base. And, oh, it's not HPR. That's an abbreviation anyways. Okay, so our weak acid is HNO2. And then the salt is NaNO2. Okay, we want to know what volume do you need for the weak acid, and what volume do you need of the conjugate base, so that when you mix them together and add up their volumes, you have 1 liter of buffer. Okay, so with this in mind, then we want to know the ratio. We are told that the buffered solution that we want is 3.55. And we're going to need the pKa of the nitrous acid. So I need to look up that value. I need to look up the Ka. Sorry, I should have done that before. Gives you a chance to think about what we're up to. Okay, so for HNO2, the Ka is 4.0 times 10 to the negative 4. And at this point, you should know how to do your pKa's. Hopefully that's easy now, just negative log. Okay, so we want a pH that's higher than pKa. So I want you to take note of that. That means you're going to need more base than weak acid. So let's notice that we're going to solve for this ratio. So pH, going to subtract pKa and then take the antilog. So 10 to the pH 3.55 minus 3.40. And I believe in class or Zoom, we got 1.4. So that has to make sense. The ratio of A minus to HA is greater than 1. And that makes the pH a little bit more basic from the pKa. Okay, so now what I want you to think about is how we're going to solve for these volumes that were being asked. And what I want you to picture is that the amount, the molarity we start with. So if I take the 0.50 molar and I multiply by how much I need, I'm going to mix them together, right? And our final volume will be a liter. So that's really the concentration of the weak acid that's going to be in our buffer. And then for the other one, same thing, except it's for the salt. Where'd I get the 1 liter? Is it asked to make 1 liter of buffer? Okay, and then we're going to plug it into here. So if you notice, when I do the ratio, that 1 liter is going to cancel out. So I'm not going to show that. Oh, hold up. It's base on the top always. Okay, and then the other thing you should notice is that the 0.5s cancel. So really it's a volumes ratio. Now here's where we have to do some algebra, but I want you to think of it conceptually. What this is saying is we have a ratio of base to acid of 1.4 to 1. And then the other thing is we need 1 liter. So let's just pretend that our ratio was 1 instead. So let's say that's our ratio instead of that. So I can just show you how you should think of it. Oops. Oops. Uh-oh. Okay, I'll stop messing with it over there. How about I show you over here? So our ratio is 1 of base volume to acid. Then in 1 liter, that would mean 500 milliliters of each, or 0.5 liters of each. Because then they'd add up to 1 liter. So if it's 1.4, I made a guess in the Zoom discussion that I was thinking we were going to come in like this, like 600 to 400. That was my guess. Let me see what I get with that. That's 1.5. That would have been my guess. So now I have to figure it out because it really should be 1.4. But I'm hoping that you kind of see what we're up to. It is how much of each do we need to get this ratio, but we want that volume of buffer. So to officially solve this, that was my guess. Then I just need to do a little bit of algebra, which is that I'll call the volume of the base. So X will be the volume of base. And then I'll call the bottom one Y. That's going to be the volume of acid. But I know that they equal, when added up, they equal 1 liter. Okay, so I'm going to erase this top part so I have a little more room. So this is what this would look like. 1.4 equals X over 1.0 minus X, right? Because if I solve for X, X is equal to 1.0 minus, Y is equal to 1.0 minus X. Because we can't have two unknowns, right? So we're making a substitution there. So if I solve for this, 1.4 times 1 minus X equals X. That's 1.4 minus 1.4x equals X. And then this is like a 1 there. So I'm going to add that to the other side. We get to see how close I was. I was guessing 600 milliliters or 0.6 liters. And it was 0.583 or 0.58 liters. That's 580 milliliters. And then the other one then would be 1 minus that, which is 0.42. So the volume of base that you needed here was 0.58 liters. And then the other one was 1 minus that, 0.42 liters. And then if you want to double check yourself, you'd plug in to make sure that the ratio of this one to this one is 1.4, which it is.